In this video, we are going to look at how we can predict whether a precipitate will form and how we can selectively precipitate out solutions. So let's look at how we can predict the formation of a precipitate. So a saturated solution is a solution that has the maximum amount of solute. It has the maximum amount of solute. So you can't add any more solute to your solution. If you did, the solute would precipitate out. Now, if you have an unsaturated solution, it means that you don't have the maximum amount of solute and you can add more and have it be soluble. So we can use Q and compare it to K to determine whether a precipitate will form or not. So just like we use Q to predict which way a reaction will shift, and when we compared it to K, we can do the same thing here. So when Q is equal to K, it means that we have a saturated solution. And no change will occur. So just like before, when Q was equal to K, it meant we were at equilibrium. That's what we have here. Now, when Q is greater than K, then a precipitate will form. Until you get a saturated solution. If Q is less than K, then no precipitate will form. The solution is unsaturated. So let's look at an example of how we can evaluate this. So does a precipitate form when 0.1 liters of a 0.3 molar calcium nitrate solution is mixed with 0.2 liters of a 0.060 molar sodium fluoride solution. So the first thing I want to do is figure out if a precipitate will form. Well, I need to know which precipitate will form. So when I look at the reaction between calcium nitrate and sodium fluoride, it will form two salts. So this is a double displacement reaction where calcium is going to form a compound with fluoride and sodium is going to form a compound with nitrate. Now, I know that sodium and nitrate are always soluble, and so this calcium fluoride is going to be the salt that I am curious if it will form a precipitate or not. So I am going to get the equation, the dissociation equation for calcium fluoride. And this is going to be a 1:2 mole ratio where it breaks up into calcium ion plus 2 fluoride. So in order to do this problem, I need to calculate the concentration of calcium ion and the concentration of fluoride. And then I can calculate QSP. So calcium ion I am going to have 0.30 moles of my calcium divided by 0.300 liters. Remember, I had 0.1 liter of the calcium nitrate solution and 0.2 liters of the sodium fluoride solution. So I'll have a total of 0.3 liters. So this will give me 0.1 molar calcium, because in every 1 mole of calcium nitrate, I have 1 mole of calcium. Now I need to calculate the concentration of my fluoride ion. So this is going to be 0.0 0.60 divided by 0.300. And when we plug that in our calculator, we get 0.040. So now I can calculate Q. So Q is going to be the exact same. We're going to calculate it in the exact same way that we would calculate our KSP. So we will get 0.10 times 0.040 squared. So QSP is equal to 1.6 times 10 to the negative 4. I can go to my book and look up the value for KSP of calcium fluoride. And when I do that, I can see that KSP is 3.2 times 10 to the negative 11. So when I compare the two, QSP is greater than KSP. So when that happens, a precipitate will form. So calcium fluoride will precipitate. Now we can also take a solution and do what is called a selective precipitation. And a selective precipitation is a method used to separate ions. And we have to use KSP in order to do this. So let's look at an example of how we would set this up. So an aqueous solution that is 2 molar silver nitrate is slowly added to an aqueous solution containing 0.011 or 0.0100 molar chloride and iodide. Which ion will precipitate first? So the very first thing I need to do for this problem is I need to compare the KSP values for silver chloride and silver iodide. Now keep in mind that we have ions in the solution. So those ions are going to react with the cation. They're not going to react with the other anion. So that's how I can figure out which precipitates I'm going to look at. Now, the KSP for silver chloride is equal to 1.8 times 10 to the negative 10. And the KSP for silver iodide is equal to 8.5 times 10 to the negative 17. So the silver iodide has a KSP that is much, much smaller than the silver chloride. So silver iodide will precipitate first because it has a smaller KSP. So the thing with the smaller KSP will precipitate first because it is going to prefer the reactant side. And like we said, the reactant side is going to indicate the insoluble. So what we can do is we can go through and calculate the concentration of the iodide and the chloride that is going to be required in the solution. So I can set up my rice tables. And something you need to keep in mind is we have a starting concentration of our silver. It is 2 molar. We don't have a starting concentration of our iodide quite yet. We have to see what that the minimum concentration is in order to see when it will start precipitating. So this is going to be plus S. So at equilibrium, this is going to be 2 plus S and S. So my equilibrium expression is going to be KSP is equal to the concentration of silver times the concentration of iodide. So this will be 2 times S. And that is going to be equal to 8.5 times 10 to the negative 17. So S is equal to 4.25 times 10 to the negative 17. So this is the concentration of the iodide that is required to start precipitating out the silver iodide. Now we can do the same thing for the silver chloride. Notice it's going to have the exact same pattern, except now we'll use chloride instead of iodide. But the KSP is still going to be silver times chloride. Silver is still going to be 2 molar. Chloride is still going to be S. And this is going to be equal to 1.8 times 10 to the negative 10. So the molar solubility is going to be equal to 9 times 10 to the negative 11. So what this tells me is when the concentration of my iodide is at 4.3 times 10 to the negative 17, that's when I will start to see a precipitate form, and that precipitate will be silver iodide. It's not until we see a concentration of 9 times 10 to the negative 11 that we will get a precipitate of silver chloride.